Hello students. So in the previous video we discussed about discrete time Fourier transform and its properties, and we took some examples, some basic problems and some problems using properties of DTFT we have solved. And in this video we'll start the new topic, that is Z transforms. So this comes under module 5. Now the Z transform is similar to the discrete time Fourier transform. That is, we are transforming the signal from one domain to another domain. Here we are using Z transform for that. Now Z transform is the extension of discrete time Fourier transform, which represents the discrete time signal in frequency domain. Suppose what is the difference between that? That is the main thing we are to deal with here. Now for a complex signals, we can the Z transform. So in the Z plane we can represent these values, the Z plane, and we can consider finite duration signals, infinite duration signals. The approach will be slightly different from each finite and infinite duration signals. So that we will see, and this also deals with the properties and some problem related to the properties and all. Now if you consider an impulse response h of n from an LTI system, now the Z transform of this is represented as h of z, and it is given as h of z summation n is equal to minus infinity to plus infinity h of n z to the power of minus n. This one, when applied to a system, when h of n is applied to a system, the output will be y of z is equal to h of z to the power of plus n. So this is what we are going to get for the system output. Now if we consider for the same thing for an input x of n, the Z transform is given as x of z is equal to summation n varying from minus infinity to plus infinity x of n z to the power of minus n. So this is what we use as a definition of Z transform, where this Z is complex variable, and this Z is noted as Z is equal to R e power j omega. So what is this R? So this is the magnitude of Z, and omega is the angle of Z. So this is, if you consider the Z plane, since it is complex variable, so we have the imaginary and real part. So at this point, if this is Z in the Z plane, then this distance is R. We can also call this as the radius, and the angle here that is created is omega. So this value is R e power j omega, which is nothing but Z. Okay, so this is the Z plane, and this one is imaginary and this one is real. axis. Now in this z plane, so if this point is the value of z, so that is r into power j omega, this r will be the distance from the origin to this point, and the angle is angle created is omega of z, that is angle of z. And in this concept we have one more thing to deal with, that is the region of convergence. The region of convergence, short form is ROC. So what is this region of convergence? So this means if you observe this equation 3, so the region of convergence defines the region where Z transform exists. ROC means the region of convergence defines the region where Z transform exists. Okay. Now the set of values, if the set of values, a set of values means those are nothing but the Z values. The set of values of Z that causes the system output to converge, that will lie in this ROC. So the values will be lying in this ROC region, so that will make the system output to converge. So converge means they will meet at some point. That is the meaning. So the overall definition, so based on this we can define the ROC as the range of Z for which the Z transform converges. And since this Z transform is a power series, so it converges, this Z transform converges when this x of n z to the power of minus n is absolutely summable. That is, we can represent this summation n varying from minus infinity to plus infinity x of n z to the power of minus n. So this value should be less than infinity. Absolutely summable means less than infinity. So then only this system, that is the ROC, can be defined. So in equation 3 we have x of n z to the power of minus n, whatever the term inside the summation, if it is absolutely summable. Summable means it will be a finite value. Then only the z transform, that is x of z, will converge. Okay, and where it will converge, that will lie in the region of convergence. The values of z which allows the system to converge will lie in the region of convergence. Okay, so that is the meaning of it. Now this region of convergence, we have to define that. That means it will defines where Z transform is. So whenever Z transform is found, we have to mention the region of convergence. Okay, for that let's have some examples on this. So we take some finite duration signals and some infinite duration signals as well. So first we'll start with the Z transform and ROC for finite duration. Okay. Now consider x of n is 0 for n less than n naught. So this n naught is a positive or negative value, but it is finite. Okay. So n naught is maybe a positive value or negative value, but it is a finite value. So based on that, in the first case, if this n naught is greater than or equal to 0, that is positive, then so x of n is a positive time sequence, and this ROC lies in entire, or ROC is entire Z plane except at Z is equal to 0. So that is the condition is find like this. So that means if we have a n naught greater than or equal to 0, so it will be considered as positive time sequence, and the region of convergence will be the entire Z plane except at the origin, and that is Z is equal to 0. So that's why this ROC lies above 0. That means greater than 0 means only for the positive durations, greater than 0. Next, if n naught is less than 0, then x of n is a negative time sequence, and this ROC is entire Z plane except at Z is equal to infinity. That is, the value of Z will be less than infinity. So here, if it is a negative value, that means if n naught is negative or negative time sequence, the region of convergence will be entire Z plane, but except at Z is equal to infinity. That means it will acquire entire Z plane, but the value of Z will be less than infinity. So that's why it is mentioned as except at Z is equal to infinity. Okay. So to understand this, we'll take some example here, how to find the ROC and how to find the Z transform of the signal. Okay. So we'll take an example. Consider the sequence given x of n is equal to 1, 2, 2, 1, where 1 is the origin. Now the point is obtain ROC for the given sequence. Now you have to identify whether it is right-sided or left-sided sequence, or in other words, positive time sequence or negative time sequence. Now looking at the signal, we have the origin here, and the signal is from 0, 1, 2, 3. So looking at the signal, we can say it is positive time sequence. So let's find out. X of z is equal to, from the definition of Z transform, we can write it like this: x of n z to the power of minus n. Since the signal is present from 0 to 3, so the limit changes from n is equal to 0 to 3, x of n z to the power of minus n. Now if you elaborate this, x of 0 z to the power of 0, x of 1 z to the power of minus 1, plus x of 2 z to the power of minus 2, plus x of 3 z to the power of minus 3. So next, substitute the values x0, x1, x2 and x3 here. So x0 value, x2 value is 1, x of 1 value is 2, x of 2 value is 2, and x of 3 value is 1. So let's substitute here. 1 z to the power of is 1, 1 into 1 is 1, plus 2 into z inverse, plus 2 z power minus 2, plus 1 into z power minus 3. So this is x of z. The condition says if it is a positive time sequence, then the ROC means the values of z will be greater than or equal to 0. Okay. So here ROC will be greater than 0. I'm just giving the example for a positive time sequence. Now consider this x of n is equal to 1, 1, 2, 2. So this is the origin here. Find ROC. Now if you apply x of z is equal to, now if you elaborate this, substitute first x of n. The limit, if you look this, here is origin, so -3, -2, -1. So -3 to 0, x of n, z to the power of minus n. So apply the value x of -3 z power 3 plus x of -2 z power 2 plus x of -1 z plus x of 0 z to the power of 0. Now x of -3 value is 1, -2 is 1, -1 is 2, and x of 0 is 2. So 1 into z power -3 is z power -3 plus 1 into z power -2 plus x of 1 is 2 into z plus x of 0 is 2, z to the power of 0 is 1. So this is x of z. Now this is a negative time sequence, so the ROC will be less than infinity. So this is a finite values we are considering here, means we know the starting and end point of the signal. Now for this one we have 2, 1, 1 and 2. Here is the origin. Next, find ROC. Now to find the ROC, this is origin, this is -2, -1, 0. So this is, sorry, this one is 1. Now x of z is equal to summation n is equal to -infinity to +infinity x of n z to the power of -n. So that gives summation n is equal to -2 to +1 x of n z power -n. Now if you look at the signal, we have both positive and negative values, and that means positive sequence and negative time sequence both are present in this one. Okay. So now if you substitute, x of -2 is 2 and x of -1 is 1, x of 0 is 1 and x of 1 is 2. So 2z square plus 1 into z is z plus x of 1 into 1 is 1 plus 2z inverse. So this is x of z. If you observe this, we have positive time sequence and negative time sequence. So the positive time sequence is z is greater than 0 and the negative time sequence is z is less than infinity. Since both of them are here, are present in this signal, therefore z will be present in between 0 and infinity. So this is the region of convergence. So that means between 0 and infinity, the values of z will converge. That is the meaning here. Now we'll take some infinite duration signals. So we'll take z transform and ROC of infinite duration here. Now before going to that, I just want to clear a concept called poles and zeros. Now these poles and zeros, so they will give graphical representation of rational transfer function in complex plane. So that means in signal processing, or in controls system control theory and all, the poles and zeros gives the graphical representation of the transfer function, and this transfer function will be rational in nature. Now the transfer function can we represent in z plane or any complex plane. We can represent in S plane as well as the Z plane. So why we can if for this it is helpful in conveying the information, why in certain cases like the properties of system, like whether stability or causality property, we can obtain the information from this. And in the region of convergence also, the poles and zeros play an important role. So we use locating poles and zeros in region of convergence, because so the properties of ROC says no pole should be present in the region of convergence. So that is the reason here. Now these poles and zeros usually present in the infinite duration signals, and as I mentioned, it is the transfer function, rational graphical the representation in the complex plane. How? As a rational transfer function, so we represent this x of z in poles and zeros means p of z divided by q of z. That means the rational form is p by q. So in Z transform, it is p of z by q of z, where the numerator of the expression will give you the location of zeros, and the denominator will give you the location of poles. Okay, and as in the previous case here, also we are considering the positive time exponential sequence. So we are going to find the Z transform of this, and we are going to find the ROC. Okay, so let x of n is equal to alpha n into u of n. So it is positive time sequence, so that's why I have taken positive time exponential. Alpha n will be an exponential sequence, and u of n is present only for positive time, because u of n is equal to 1 for n greater than or equal to 0, and it is 0 for n less than 0. So this is the reason. Therefore, so x of z is equal to summation n varying from minus infinity to plus infinity x of n z to the power of minus n. So x of n is alpha n u of n z to the power of minus n. Now u of n is present for only positive values of n, so therefore the limit changes from n varying from 0 to infinity alpha n into z to the power of minus n. So if you combine this, alpha and z have common power, so you can combine this. So this is my x of z. Now from geometric series, we have summation n is equal to 0 to infinity a to the power of n can be written as 1 divided by 1 minus a, where a is less than 1. So this condition will also helpful in dealing with the ROC. So what does it say? If you apply this, in place of a we have alpha z inverse. So that's why 1 divided by 1 minus alpha z inverse, where alpha z inverse is less than 1. Now if we simplify this, 1 divided by 1 minus alpha by z, so that is z minus alpha divided by z 1, or you can write it as z divided by z minus alpha. So this is x of z. Now the region of convergence, it says x of z will converge if see this term, what do we have here? If alpha z inverse less than 1, if this is satisfied, okay, so that is the meaning of this. Or if this condition satisfies, then alpha z inverse. Now if you simplify this, alpha z inverse less than 1, so that is alpha by z less than 1, so that implies alpha is less than z. So rearranging this, z is greater than alpha. So that means in the z plane, the value of z, that means the point where the signal converges, is will be greater than alpha. Now this alpha will give you the radius of the circle, whatever the values it take. This is called the unit circle. Now the value, or yes, the radius value is alpha, and the ROC lies greater than alpha, means so above this circle. So here is the region where the ROC lies. So do mention this ROC, okay, and this is the Z plane. So we have to locate graphically like this, okay, put the shades like this, and it should not touch this, okay. For positive time sequence, as you can see, the for positive time sequence, this Z is not present near the origin, so that is important. As you can see, the value of Z is, it will be greater than 0, but it will be the entire Z plane except at Z is equal to 0. This is the meaning of that. Next one, we'll take a negative time sequence. Negative time exponential sequence, okay. So x of n is equal to minus alpha n u of minus n minus 1. So it is a negative time sequence. So why I have taken this? So when taking the limit, you'll understand. So x of z is equal to summation n varying from minus infinity to plus infinity x of n z to the power of minus n. So if you substitute that, x of n minus alpha n u of minus n minus 1 z to the power of minus n. Now u of minus n minus 1 is 1 for minus n minus 1 greater than or equal to 0, and it is 0 for minus n minus 1 less than 0. So this gives the limit as n less than or equal to minus 1, and this gives for n greater than minus 1. Okay, and simplify that. That means the for values of n which is less than minus 1, u of minus n minus 1 will be present. So that means our limit changes from minus infinity to minus 1 I'll take this minus outside, alpha n z to the power of minus n. Now minus I'll take as it is. If I interchange this, n is equal to 1 to infinity, then it will be alpha to the power of minus n, z to the power of plus n. So I did this for my convenience. So minus n is equal to 1 to infinity alpha inverse z whole to the power of n. Okay. So from geometric series, we have this term. One is varying from minus infinity to plus infinity. So this can be written as a divided by 1 minus a, where a is less than 1. So this is the term we have. Now applying this, we have minus alpha z, alpha inverse z divided by 1 minus alpha inverse z. Okay. So this we can write it as by removing this minus alpha inverse z divided by alpha inverse z minus 1. So to eliminate that, I can take z by alpha divided by z by alpha minus 1. So that gives z by alpha here. This alpha gets cancelled. So you remain with z divided by z minus alpha. Now you will get the same term as in the previous case, but coming to this ROC, so x of z will converge if what is the condition? So here you can see the condition in place of this alpha inverse z. If alpha inverse z less than 1, if this condition is satisfied, so therefore alpha inverse z less than 1, z by alpha is less than 1, so that gives z less than alpha. So here z lies value will be less than the alpha. So we have a circle with the radius alpha. Now this z value is less than alpha means this region of convergence will lie here. So this is ROC. Now if you remember the region for negative time sequence, this ROC is entire z plane except at z is equal to infinity. That is what it says. So that means the value of z will be less than infinity. And see in this diagram graphically, it is the entire z plane. It is, but it is not present at z is equal to infinity because it is some finite value. Okay. So this is the region of convergence, how we represent. Now in the third case, we'll take x of n is equal to minus u minus n minus 1 plus 1 by 2 to the power of n into u of n. Same thing. So find ROC and locate poles and zeros of x of z in z plane. So if poles and zeros are asked, then you have to find the location of poles and zeros. That is a mandatory thing here. If not, you can stop at ROC. If the location is asked, you have to equate the equate x of z to both numerator and denominator to 0, and then we have to locate the poles and zeros here. So that we'll see in this problem. Now if you observe this, it is the combination of two signals. One is a negative time signal, another one is a positive time signal. So both are combined here. Now how you are going to plot the ROC in this case? So let's see that. So x of z is equal to summation n is equal to 0 to infinity x of n z to the power of minus n. So substitute that. N is equal to minus infinity to plus infinity minus u of minus n minus 1 plus 1 by 2 to the power of n into u of n z to the power of minus n. So you can split this because this is present for summation n varying from minus infinity to minus 1, u of minus n minus 1 z power minus n, plus this term is present for n is equal to 0 to infinity 1 by 2 n u of n z power minus n. So for this entire duration, this signal is 1, and for this entire duration this signal is 1 here. Since minus u of n minus 1 is there, the value will be minus 1. N is equal to minus infinity to minus 1 plus n is equal to 0 to infinity 1 by 2. I am combining both, 1 by 2 z inverse to the power of n. Okay, or you can skip this one if you want to, or you can write 1 by 2 n z power minus n. Next thing, this minus I'll just take it out here, minus, and I'll interchange the summation. So n is equal to 1 to infinity z to the power of plus n plus summation n is equal to 0 to infinity 1 by 2 z inverse whole to the power of n here. Now applying geometric series, this one is from 1 to infinity and this one is from 0 to infinity. So that's why this will become minus z divided by 1 minus z plus 1 divided by 1 minus 1 by 2 z inverse. And first one is z less than 1 and 1 by 2 z inverse less than 1. So these are the conditions that we took in the last two examples. You can say now to eliminate this 0, I'll write this as z divided by z minus 1 plus 1 divided by 1 by, so that will give you 1 by 2z. Yes. Now let's keep on simplifying this term. Z divided by z minus 1. I think that is applicable for, is it for entire signal? No, just for this term. Now if you take the LCM of this, this one is 1 minus 2z is there. Let's try to simplify this. So I'll write the simplified version, z divided by z minus 1 plus here z divided by z minus 1 by 2. Yes, you can write it like this. If we take the LCM, z minus 1, z minus 1 by 2. So this is just a simple simplification process, plus z into z minus 1. and if you go, you should get 2z square minus 3 by 2z divided by z minus 1 and z minus 1 by 2, and you can further take z outside, that will leave 2z minus 3 by 2 divided by z minus 1, z minus 1 by 2 here. Now this is the least we can simplify. Now we have to locate poles and zeros, and before going to that, we have x of ROC, we have to find ROC. X of z will converge if the first condition is z less than 1 and second one is 1 by 2 z inverse less than 1. So this one is fine. If you simplify this, you will get z greater than 1 by 2 and z less than 1 by 2. So for this one, so let me write it here. Z greater than 1 by 2. Now if you observe, the location of z is greater than 1 by 2, less than 1. So this is where ROC lies. So this is first point. Next, coming to poles and zeros. So as I mentioned, equate the denominator to 0, you will get poles, and equate the numerator to 0, you will get zeros. So in x of z, the denominator, so poles, z minus 1 is equal to 0 and z minus 1 by 2 is equal to 0. So z is equal to 1 and z is equal to 1 by 2. So the location of poles are z is equal to 1 and z is equal to 1 by 2. Coming to zeros, equate the numerator, that is this term, to 0. So z into 2z minus 3 by 2 is equal to 0. If you can split that, that is z is equal to 0 and 2z minus 3 by 2 is equal to 0. 2z is equal to 3 by 2, and if I cross multiply, z is equal to 3 by 4. So at z is equal to 3 by 4 and at z is equal to 0, we have the location of zeros, and z is equal to 1 and at z is equal to 1 by 2, we have poles. So let's draw this here. Now observe this, we have two conditions. We have two circles with radius 1 by 2 and 1. So we have two circles that we have to draw here, because we have both positive time sequence and we also have a negative time sequence. So that's why. Now these are the two circles with radius so this one is having a radius 1 by 2, and this one with radius 1. Now where is ROC locating? So the ROC is located between 1 by 2 and 1. So this is the region greater than 1 by 2 but less than 1. So this place we have our ROC. Now I will use some other colors to locate. Now coming to poles, you can see poles at z is equal to 1 and z is equal to 1 by 2. Here we have z is equal to 1. So poles are located using X mark exactly on the line, and zeros are located at 0 and 3 by 4. So we locate 0 by writing 0 here. One is at the origin and another one is 3 by 4. So 3 by 4 is in between 1 by 2 and here. So here I am mentioning that. So these are poles, these two, and these two are zeros, where 0 and 3 by 4, that is the location of that. Poles, where are they? 1 and 1 by 2. So this is the origin. Now this is the z plane we are going to get, and this region is our ROC, the region of convergence. So that means we call this consider with this condition as where both positive and negative time sequence are there. Then the ROC is present, that is in concentric. Concentric means between two circles. So that is the region where our ROC lies. So we have taken the positive time sequence and we have taken the negative time sequence, and then we also considered the condition where we have both positive time sequence as well as negative time sequence. And I just want you to try some problems here on your own and try to locate the ROC here. So this one you just try at home. So the first one, all of them. So the problem is like this: find Z transform and determine ROC for the following signals. So the first one is x of n is equal to 1 plus n into u of n. You have to find the Z transform and you have to locate ROC. And second one is x of n is equal to a to the power of n plus a to the power of minus n into u of n, where a is real. Third one, x of n is equal to minus 1 to the power of n, 2 to the power of minus n into u of n. So just want you to try these three problems and try to determine the ROC for that. Okay. Hope you have understood this method, and if you have any queries, whether in locating ROC or any other point, so do reply or comment in this video. Okay. So thank you for watching.